Let us start chapter 2, module 1. In the first module, we will discuss a topological property which is the probably most common topological property, that is called metrizable property. Most of the topological space we know are metrizable. In the metrizable topological space, we can use our usual definition of continuity using Hens continuity criteria and also usual definition of convergency. That is the reason metrizable topological spaces are very much important. So, how topology comes from the metri property, it will be shown in our module presentation. As we have already mentioned that one of the most important topological spaces are metrizable topological spaces. Topology of such spaces have to be defined in terms of a metric on the set. Topologies given in this way lie at the heart of modern analysis. In this section, we shall define the metric topology and shall give a number of examples. In the next section, we shall consider some properties that metric topologies satisfy. So, let us start with the definition of a metric. Let X be a non-empty set. By a metric, we mean a function d from x cross x to R which satisfy some distance conditions. That means d of xy greater or equal to 0 for all xy belongs to capital X. Number 2, dxy is equal to dyx for all xy belongs to capital X. Number 3, dxy less or equal to dxz plus dzy for all xyz belongs to capital X. So, what is the first condition? The first condition says that if 2 points distance between 2 points are always positive, in fact always non-negative, and distance between them is 0 if and only if they are equal. What is the meaning of the second condition? The second condition means that the distance from x to y is equal to the distance from y to x. And what is the meaning of the third condition? The third condition says that distance of xy less or equal to distance of xz plus distance of zy, that is triangle inequality. Sum of two sides is greater or equal to the third side of a triangle. Now, given a metric d on a set capital X and some positive real number r greater than 0, let us define open ball determined by the metric d and the real number r at the point x denoted by bdxr is equal to all y belongs to capital X such that distance of y from x is strictly less than r. So, now we will say how we get a basis from metric for some topology. Proposition: let D be a metric on a non-empty set X, then the collection of all R balls BDXR for X belongs to capital X and R greater than 0 is a basis for some topology on capital X. The topology induced way is called metric topology induced by D. Proof: the first condition for a basis is trivial In fact, x belongs to BDXR for all r greater than 0. And now we say that y, if y is a point of the basis element BDXR, then there is a basis element BDYS centered at y that is contained in BDXR. Let us define small s to be the positive number r minus dxy. Then BDYS is subset of BDXR for if z belongs to BDYS, then dyz less than r minus dxy, from which we can conclude that dxz less or equal to dxy plus dyz, which is strictly less than r. Now we will be able to prove the second condition for a basis. So let B1 and B2 be two basis elements and let us choose some y in their intersection. We have just shown that we can choose positive numbers r1 and r2 so that BYR1 is a subset of capital B1 and BYR2 is a subset of capital B2. Now letting R less than minimum of R1, R2, of course it will be greater than 0, we conclude that BYR is a subset B1 intersection B2. This concludes the proof that the collection of open R balls is in fact a basis for some topology on capital X. Now we are in a situation to define metrizable spaces. A topological space X is said to be metrizable if there exists some metric D on that topological space X such that the set of all open balls is the basis of the given topological space X. A metric space is a metrizable space X together with a specific metric D that gives the topology of X. In the following discussion, we shall provide various examples of metrizable space. Very important topological space is discrete topological space. Though the most important topological space are Euclidean spaces, that means the distance metric on Rn, we will come to that later. Before that, let us start with the discrete metric. So what is discrete metric? By discrete metric on a set X, we mean a metric D defined as dxy is equal to 1 if and only if x not equal to y, and dxy is equal to 0 if and only if x is equal to y. That means distance of any 2 points is equal to 1 if and only if they are different, and distance between any 2 points is 0 if and only if they are equal. Thus metric is called discrete metric, and the topology generated by discrete metric is called a discrete topological space. Note that if we take R less than 1, then for any small x in capital X, the open ball BXR is just the singleton set small x, and if r greater than 1, then for any x in capital X, bxr is equal to capital X. So, what does that mean? That means every subset of a discrete topological space is open as arbitrary union of open set is open. So, this is the beauty that in a discrete topological space every subset is open. For example, if we consider Z the set of all natural numbers, it is equipped with the discrete topology. If we take the subspace topology of R on Z, we get the discrete topology. Now, we know that boundedness is a metric property. That means we can define boundedness in a metrizable space or in a metric space. If a subset in a metric space is called bounded, if it is called in a open ball. The question whether boundedness is a topological property also. In our following discussion, it will be established that boundedness is not a topological property. That means it is possible that two homeomorphic metrizable space, which one of which is bounded and another of which is not bounded. Let us come to the following proposition. Let capital X be a metric space with a metric D. Let us define rho from X cross X to R by the equation rho xy is equal to minimum of dxy1. Then rho is a metric that induces the same topology on D. In fact, rho is called the bounded metric of D. For the proof, first we have to prove that rho is in fact a metric. Then we shall show that the topologies generated by the matrix D and rho are equal. To prove that rho is a metric, the first two conditions, that is rho of xy greater or equal to 0 and rho of xy is equal to 0 if and only if x is equal to y, is obvious, and also the condition of symmetry is also obvious. We have just to check the triangle inequality. If rho xy or rho yz are greater or equal to 1, then obviously rho xz less or equal to rho xy plus rho yz, because in this case the left hand side less or equal to 1 and the right hand side greater or equal to 2. So, let both rho xy and rho yz are strictly less than 1. Then we have dxz less or equal to dxy plus dyz by triangle inequality, which is equal to rho xy plus rho yz. Now, since rho xz less or equal to dxz, the triangle inequality follows for rho. This proves that rho is in fact a metric called bounded metric of D. Now we will show that the topology generated by rho and topology generated by D are equal. Consider the collection of R balls with R less than 1, which forms a basis for the metric topology. For every basis element containing X contains such an R ball centered at X, it follows that D and rho induce the same topology on capital X because the collection of R balls with R less than 1 under these two metrics are the same collection. We have already told about the Euclidean metric. So, what is Euclidean metric on Rn? Euclidean metric is defined as, let x and y be two distinct points in Rn. That is, x is equal to x1, x2, xn and y is equal to y1, y2, yn. Then distance between x and y is equal to root over of x1 minus y1 whole square plus x2 minus y2 whole square up to xn minus yn whole square. This is the usual Euclidean metric. Another important metric on Rn is the sup metric. Sup metric, if we denote it by rho, then sup metric is defined as rho of xy is equal to supremum or maximum of x1 minus y1 its modulus, comma x2 minus y2 its modulus, comma up to xn minus yn its modulus. In our discussion, we will show that both the sup metric and Euclidean metric generates same topology on Rn, which is equal to the product topology on Rn. We have already known what is product topology. Product topology is the product of basic open sets. Here basic open sets on Rn are basically rectangles. So in the next lecture, first we prove that the topology generated by sup metric, topology generated by Euclidean metric and the product topology, all these three topologies are equivalent. We have already discussed about the Euclidean metric dxy and the sup metric rho xy. Our target is to prove that these two metrics are equivalent. That means topology generated by these two metrics are equal. We will require the following lemma, which in fact we have already told in some another form. Lemma, let D and rho be two metrics on the set capital X and let tau 1 and tau 2 be two topologies induced by D and rho respectively. Then tau 1 is finer than tau 2 if and only if for each x in capital X and each r greater than 0 there exists a real number x greater than 0 such that the open ball generated by the rho matrix centered at x with radius s is contained in the open ball centered at x of radius r generated by the metric D. Now we come to the proof that sup metric, Euclidean metric and product topology on Rn are equivalent. So the theorem says that the topologies on Rn induced by Euclidean metric D, square metric rho and the product topology are equivalent. The proof is calculative. Let x, y belongs to Rn, then the following inequality can be observed easily. That is, rho xy is equal to maximum of x1 minus y1 comma x2 minus y2 up to xn minus yn less or equal to dxy is equal to root over of x1 minus y1 whole square plus x2 minus y2 whole square plus up to xn minus yn whole square. Also we have dxy less or equal to root n rho xy. This can be calculated easily. Therefore, from the first inequality we have B dxr subset of B rho xr for all x belongs to capital Rn and r greater than 0. Similarly, the second inequality shows that B rho xr by root n subset of B dxr for all x and r. It follows that the topologies generated by these two metrics are the same. Next, we show that the product topology is same as the generated metric rho. Now let capital B be a basic open set in the product topology of Rn. That means capital B is the form of n open intervals product. That is, capital B is equal to A1 comma B1 Cartesian product A2 comma B2 up to Cartesian product AN comma BN. Then for each I there exists some epsilon I such that xi minus epsilon comma xi plus epsilon is contained in ai comma bi. Let us choose epsilon is equal to minimum of epsilon 1, epsilon 2, epsilon n. Then bx epsilon is subset of B. That is, B rho x epsilon. As a result, the rho topology is finer than the product topology. That is, rho topology contains the product topology. Conversely, let Bx epsilon be a basis element for the rho topology or sup topology. Given y belongs to B rho x epsilon, we need to find a basis element capital B for the product topology such that y belongs to B subset of B rho x epsilon. Therefore, if we take B is equal to product of I is equal to 1 to n y minus epsilon comma y plus epsilon, then this proves that product topology is equal to sup topology. So this concludes that product topology, sup topology and our Euclidean topology, all these three topologies are equivalent on Rn. Next, we try to some infinite generalization of the facts which we have already discussed. What happens if we try to do an infinite generalization? Naturally, for infinite generalization, we try to produce the dxy, we try to propose dxy as equal to root over of summation of xi minus yi whole square. But there is no guarantee that this series converges. So, this proposed definition of dxy in the infinite product of R is not well defined. Similarly, for soup topology, if we define rho xy is equal to supremum of modulus of xi minus yi, then the supremum may not exist. So, also in this way we can't define soup topology. So, we have to think alternatively. Let us define d bar xy is equal to minimum of dxy1 for any metric d on any set capital X, then d bar will be called the bounded version of the metric d. Now let us define a metric rho on R omega by the formula rho bar xy is equal to supremum of d bar xn yn such that n belongs to omega, where d is the standard bounded metric on R. It is easy to check that rho bar is indeed a metric. It is called the uniform metric on R omega, and the topology it induces is called the uniform topology. The uniform topology on R omega is in fact finer than product topology. For the proof, let product of UN be a basic open set in the product topology. We have to show that this is also an open set in the uniform topology. So, let X be a point in the basis open set product of UN. Then, by the definition of product topology, there exist n1, n2, nk such that UN not equal to R only for this n1, n2, nk. In all other cases, UN will be equal to R. Then for each I, choose epsilon greater than 0 so that the epsilon ball centered at xni in the D metric is contained in UNI. This we can do because UNI is open in R. So, let us take epsilon is equal to minimum of epsilon 1, epsilon 2, epsilon n. Then the epsilon ball centered at X is in the rho bar metric is contained in product of UN. For if Z is a point of R omega such that rho bar xz less than epsilon, then dxn zn less than epsilon for all n, so that Z belongs to product of UN. It follows that uniform topology is finer than the product topology. We shall conclude the discussion of this module by mentioning the following theorem. This theorem says that if we take countable product of metrizable spaces, then it is metrizable. In this slide, it is done for R. but using the same technique you can prove in any metric. What we have to do, first we have to take the bounded metric of the given metric and then the proof will be continued. The proof is given in the module, you can easily complete the proof. In this module, we have discussed metrizable spaces. The notable parts are discrete topological spaces which are metrizable. The second one is Euclidean topology, soup topology and product topology on Rn are all equivalent. And the last part is countable product of metrizable spaces are metrizable. With this, we conclude this module. Let us pass to the next module.